From today onwards, I wanted to discuss about switching. So switching is used at layer 2, but also switching occurs at layer 3. So we will talk first about layer 2 switches, and these are used by Ethernet. So these use the MAC addresses to switch. And later on, a few lectures down the line, we will talk about layer 3 switches. And usually people refer to these as routers. So these will use IP addresses to switch. So what exactly is switching and why do we need it? So let's think about layer 2. So we are familiar with this situation where you have lots of devices connected to the same bus. Now we know that Ethernet uses CSMA CD. So it's possible that multiple devices might actually transmit at the same time, because of which we might have collisions. And as you can imagine, as the number of devices here becomes more and more, then there is a higher chance of collision. So this sort of a topology of the network. So topology refers to the graph formed by the particular network. So this particular topology will not scale up to more than a few tens of hosts. So if you have like 100 hosts connected to the same bus or 1,000 nodes, then probably very little communication will be possible because there will be collisions all the time. So this sort of a topology is okay when you have a few number of nodes, but not when you go into several tens or even hundreds of nodes. So what do we do? So suppose this is, let's say, computer science. Let's say that we have a particular Ethernet LAN like this, and let's say that another department has its own LAN. What we could have done is we could just connect them together with a wire and have one large LAN. But then there's the problem of scalability. There may be too many collisions. So what we do instead is that we put a switch in between. So I'm going to draw it this way. So the switch is going to connect these two LANs together. And let's say that this particular switch has two ports, which means two network connections coming in. And let's just call this port 1 and this is port 0. So what we want this switch to do is to intelligently forward frames as they come. So suppose let's say device E and F are over here, So suppose A wants to send a frame to C. Ideally the switch should not forward it, because after all C can directly hear A's message. But if A is sending a frame meant for, let's say, E or F, this switch should forward it. Okay, so that the frame goes from this side to that side. So the switch is effectively isolating these two different LANs from each other. And it's intelligent in the sense that only if it needs to forward a frame, it will do so, otherwise it will not. Okay, so if a switch automatically forwarded everything from here to here and everything that it heard on this port to this port, then it's as good as connecting the two together. I mean, it's not really performing any useful function. So essentially what the switch is doing is it's providing isolation and intelligent isolation between the different parts of the network, so that it's going to reduce collisions on both of them, right? Compared to the case where there was one single large LAN. So switches are going to provide scalability. We'll be able to connect many different Ethernet LANs together using a switch. So we said that the switch is intelligent. It knows which, let's say, whether to forward a frame or not based on what the destination address is. So how is it going to do that? So clearly it should have some sort of a forwarding table. So what would the forwarding table look like? It should have a destination field and it should have a port number. So for example, here we would want A, B, C, D to have this port number, and EF would have port number 1. So we'll see how to populate this table, how a switch is going to figure out what should be here. But suppose it has already created the table like this. Now suppose it receives a particular frame which has A as destination. Suppose the frame has heard on port 0. It checks here that anyway A is on port 0, so I've heard that frame on port 0, so I don't need to forward it, I just keep quiet. Whereas if it has heard a frame on this particular LAN coming in on port 1 and the destination in that particular frame is A, it will see that A is lying on port 0, so it needs to reproduce that same frame on this port. Okay, so it's completely exactly reproducing a frame which it heard on one port on the other one if necessary. So how does it figure out what this forwarding table is? And we want as little configuration as possible. I mean, you can manually do it. I mean, if let's say you or I were to come up with our own protocol, one thing is that we might do it a naive way. We'll say that somebody has to actually give this particular table to the switch. You know, every time you plug in a device in a particular LAN, you should manually enter the MAC address over here. Okay, so that's a naive way of doing things, and clearly that's a big headache. You would need, if every time you connect something to the LAN, you would need some system administrator to go and fill up this table for you. And if he makes some mistake, then there's going to be a big problem. Okay? So manually configuring it is not nice. It would be good if we can do it automatically using some protocol. Also, we have to worry about the case where what if somebody unplugs, let's say, this device E and plugs it in over here. Then what's going to happen? Because if the switch maintains this table forever, then we are in trouble, because after all E has moved from port 1 to port 0. So it should be able to populate this table automatically, and it should do it dynamically so that we can take care of changes in the topology. So how is this going to work? So first of all, remember that these MAC addresses are hard coded into the Ethernet cards over here, and all MAC addresses for all cards in the world should be unique. Ideally, they should be unique. So the MAC address is 6 bytes, 48 bits, and they are unique. We don't have to worry about it at all. I mean, we don't have to worry about manually configuring it. It comes with the card itself, and each company is allocated by a centralized authority, and it's allocated a range of MAC addresses which it can use for the cards that it manufactures. Right? So that's how you prevent one manufacturer from reusing the MAC address of another one. And we trust each company to use the MAC address only once. If it creates a particular card and it puts a MAC address on it, it should not reuse the MAC address for another card. So there's no configuration required for this MAC address. It's directly there. It's hard coded in the card itself. So all of these have unique MAC addresses, and each port here too will have its own MAC address. Okay, so how would we do it? Let's think about it. Can we figure out intuitively what Ethernet does, what these switches would do? So initially the forwarding table is empty. So destination and port number, this is empty, and obviously it can't know anything before it's even connected. So now let's say that somebody plugs in these two Ethernet LANs. These two buses have cables coming from here into the Ethernet switch. Now suppose we have, let's say, A is sending it to B. Okay, so this is a frame, and this is the source address, and this is the destination MAC address, this 48-bit. So the Ethernet frame goes out, and of course everybody on this particular LAN can hear this frame. That is what we assume. Okay, there haven't been any collisions or anything, and the frame gets through. So the switch initially doesn't know where B is. I mean, the table is empty. So, but what has it learned from here? It has at least learned that A is on port 0. So that is good news. So it says that I've heard a frame originating from A on port 0. Okay, so A lies on this side. And it doesn't know where B is at the time immediately as it hears this. So what it does is, by default it forwards it on port 1. So it populates the table with this information, and it forwards to port 1. So this frame has been sent out on port 1, and of course B is not here. Okay, and as far as the switch is concerned, it doesn't know where B is. Okay. So let's say due to some reason B is going to send a frame maybe back to A or to somebody else. Maybe this frame was part of there was maybe a higher layer protocol. Maybe there's a TCP connection between A and B, something like that, and because of which B also replies to A. Okay, so suppose that happens and B sends something to A, or to somebody else, it could be to anybody else. Okay. Maybe to make it more general, let's say B sends it to C. So now what's going to happen? So now with this particular frame, what's going to happen is that the switch knows it has heard B on port 0, so it knows that B is there. And it doesn't know where C is, so it forwards to port 0. So C has directly heard this frame, and so has everybody else over here. Now suppose let's say B sends a frame to A. The switch is going to look up its table and it's going to see that A is on port 0 and I received this on port 0. So it realizes that it doesn't have to do anything because anyway A is on the same port. A would have heard the frame from B, so it keeps quiet. So don't forward. Okay, so it's a simple enough protocol that the switch listens and learns information, okay, over time. So it's going to work fine, as long as everybody speaks up, the switch will know which particular MAC address is on which side of it, on which particular port, and it will populate this table. And only for it will only forward a frame to the appropriate port if the destination is there in its particular table. Okay. So this is going to work fine. Now what if one particular node, let's say E, is unplugged from this side and put that side? Then what is going to happen? So this is clearly going to be a problem because then if let's say F sends a frame to E, the switch, if it maintains the old table, it will think that E is on this side and it will not forward it, which is going to be a problem. So what we do is that each particular entry has a particular timeout value or an expiry time. So suppose it has created this particular entry at a particular time, and let's say every time it gets a frame from F, it extends that expiry time. If it keeps hearing from F on this port 1, it will keep extending that time. But if a long time gets over and it hasn't heard from F, then it will delete this particular entry. Okay, so this is a little bit about how a particular Ethernet switch actually creates its forwarding table. Extend this situation to where we have more than 2 ports in a particular Ethernet switch. So by the way, Ethernet switches are sometimes called bridges because they're sort of bridging this particular LAN to that one. Okay, so sometimes they are called bridges. So we can generalize it. So suppose you have 4 different ports over here. And suppose initially your table is empty. So this is the destination, this is the MAC address. And this is the port. So how are we going to do this in the general case? So suppose you get a frame on port 0. Initially the table is empty, so you forward on all the ports. So if the destination is not in the table, then forward on all ports. Okay, and let's say that you have A over here. And let's say B is over here. So initially, let's say if it gets a frame from A to B, okay, it would send it on all ports and it would say that A is on port 0. Okay. So it's just going to receive this whole frame and reproduce it on all these different ports. Okay, so this generalizes the creation of this forwarding table. So we can hook up many different Ethernet LANs together and using just one particular switch. Now let's go a little bit beyond this. So so let's think that somebody is doing this. There are few departments, let's say in IIT, and we are just connecting them all together using this particular switch. Let's say each of these is on a bus LAN, right? And now, let's say that somebody else also starts connecting up LANs together using another switch. So the situation gets a little bit tricky. So let's say that there is one LAN that is connected through a switch to another LAN, and let's say the institute is more and more computers are getting installed, and let's say that this is CS, electrical, whatever, mechanical, and somebody is connecting these all together. Okay, and more and more departments, let's say, are getting more and more machines, and we want to connect them all together. So people are putting these switches like this. Okay, let's say they happen to do it in this fashion, and now somebody actually connects it up like this. So this is a particular LAN. I'm just numbering them: LAN 1, LAN 2, LAN 3, LAN 4. So in our excitement, we've been connecting these different LANs together so that machines on one LAN can communicate with machines on another LAN. Now there's a slight problem over here in that there's actually a loop over here. So suppose this is A, and A sends out a frame which has a destination which is, let's say, not there among the machines on this line. It just created a frame and it put in a destination MAC address which didn't belong to any machine here, let's say as an example. So what's going to happen? Everybody's table does not have that particular MAC address, so this one would forward it. This particular switch also has, it hears this from here and it realizes it that's not there in its destination, it will forward it here. This will forward it here and so on, this will forward it again. So the frame has gone in a full circle, it's gone in a cycle, and this switch has again heard it on this port, it again looks up its table and again forwards it and so on. So that frame is going around forever over here in this loop. Okay. So this has become an issue that frame is living forever, it has an infinite lifetime and it's sort of circulating continuously over here. So this is a problem because it's using up some resources. Okay, some amount of resources, bandwidth is being used by this frame. It very quickly is circulating round and round over here. Right? In a matter of maybe milliseconds, it's doing a full round. Okay? And maybe it doesn't affect the performance too much. It doesn't. People don't notice it. But after some time, there may be lots of these frames going around which just eats up all the bandwidth. They are forever being forwarded. So we want to avoid these sorts of loops. In fact, it happened once at IIT Delhi when I was there. Somebody by mistake made some sort of a connection like this, creating a loop, and the protocol didn't function properly. We'll look at the protocol which breaks these loops, but for some reason it didn't work properly. Maybe there was some sort of a configuration mistake of some kind, because of which the whole department network went down because of this sort of a loop. Okay, so when the professor in charge found out what was the issue, he just unplugged one of these and then everything became normal. So we want a protocol to do that. So we want to break this loop in some way. Okay, so we want to avoid loops, and the protocol that is used is called a spanning tree protocol. Which was created by a lady called Radia Perlman. Several decades ago, and her protocol has sort of become the standard. So what we want to do is that given this whole graph, we want to disable a few ports, just a few of them, so that we get rid of all particular loops and we end up with a tree, a spanning tree. So the spanning tree should be able to connect all LANs to all other LANs in this particular graph. It shouldn't leave. For example, if you disable both these ports, which I am showing here, then this LAN will be disconnected from all other LANs. That should not happen. All the LANs should be able to reach all other LANs, but we want to disable a few ports. And here you can see that disabling any one port is going to break the loop. But in a general situation with a general graph, how do we do it? And that's what the spanning tree protocol does. So how does the spanning tree protocol work? I just call it the SPT protocol. So first of all, it's going to elect a root bridge. So we want a tree, and this root bridge is like the root of that particular tree. And initially in this sort of a topology, all of these look equal to each other. So which of them is going to become a root? And that's what the election mechanism is going to do. It's going to choose one of them to be the root. So, suppose we choose that as the root. Then what do we do? Well, everybody needs to be able to connect to everybody else. So each particular bridge is going to find the shortest path to the root Okay, so each bridge finds which port is closest to the root, and it assigns this port as the root port. Okay, so let's say that suppose this is switch 1 and suppose it is the root. We look at the exact protocol, but let's just say that these numbers that I'm putting here correspond to some IDs, and let's say that switch 1 is the root and this is switch 2, switch 3 and switch 4. And to simplify things, let's just put cost, the distance between them, as just being 1 if it is a neighbor and 2 if it is a neighbor of a neighbor, and so on. Okay, but of course the protocol can generalize that, but let's say that this is of distance 1 from here, and of course this particular port, what is the distance to the root? This would be 1, 2, 3. Right, so this particular port would be distant 3 from here, whereas this is the distance 1 from there. So this ends up being the root port over here, and this also is just this particular port is closer to the root than this one, so it's going to be assigned the root port. Okay, what about this one? This seems to be equally, both ports seem to be equidistant, right? So there would have to be some tie-breaking rule, and let's say we are going to do it based on let's say the particular ID of this particular switch, which is 3, and let's say that this is the root port. Okay, so there has to be a tie-breaking rule over here. In case you have multiple ports with the same distance to the root. Okay, so we'll have to talk about that too, and now suppose a particular so this is sort of ensuring that at least all bridges have some way to get to a particular to the root node. At least they know that if I need to forward something towards the root, I need to send it on this root port. So these are the root ports which have been chosen by the various switches, and we are definitely not going to disable these when we try to break all loops. Okay, so these are going to be active ports. Okay, we are going to forward frames on them. So what we still need to do is we also want to know that suppose a frame is generated, let's say on a particular LAN, which of these different switches connected to the particular LAN are going to forward those frames on this tree that we have created. Okay. So here of course there are two choices. Here too there are these two particular switches which are which could potentially forward a frame onto the tree that we want to create. So we are going to choose only one of them to do that job, and that is called essentially a designated port. So what we do is that all bridges which are connected to a particular LAN elect one among them to forward frames on that LAN, and the port of that particular switch on that LAN is called the designated port. So let's look at this particular case over here. Let's look at this particular LAN. So one of them has to be elected to go to forward frames on this particular LAN towards the root. And which one are we going to choose here? Well, we'll have to have a rule for that. But here obviously this is the designated port which sends the frame to the root. And for this particular LAN, this is going to be the designated port. And what about for this LAN? Okay, we'll look at the exact rule for choosing this, but we need to send frames. Let's say somebody generates a frame here and it needs to be forwarded to the rest of the tree. One of these would have to be chosen. And so since this is closer, let's say we mark this as the designated port. Okay. And for this particular LAN, it's the only one remaining for which we need a designated port. And let's see, this is just 1, 2 away, this is 1, 2, 3 away. So we will choose this as the designated port. Okay, for LAN 1. Yeah, I'll just mark this designated port 1, designated port for 2. This is the designated port for LAN 3 and this is the designated port for LAN 4. Okay, so we'll look a little bit at the exact rules in a moment, but intuitively this is what we are going to do. So all the ports which are marked as root port or designated port are kept alive, they are not disabled, and any port which is not a root port or a designated port is disabled. So it's a simple enough protocol that Radia Perlman has developed, and it's quite elegant. So first we elect a root, and depending on the distance of a particular switch to a root, it will choose the port which is closer to the root, and that will become its root port. So each switch will do that. Now for each LAN, these particular switches connected to it should discuss among themselves and choose one of them to forward frames towards the root, and the port of that switch connected to this LAN is called the designated port. So we do that for every LAN, and now any particular port which is not a root port or a designated port is disabled, and you can think which port over here is of that type, and it is going to be this one. So this is going to be disabled. Okay, so when it comes to forwarding frames, suppose this protocol is completed and this one is disabled, it's just going to ignore any frames which are incoming over here, and it's going to assume as if this is not over there. It's as if this port is removed from the protocol that it's going to use henceforth. Okay, so assuming of course that the tree stays the same, right? So you might think, what happens if the root goes down and so on, right? So that they have to have additional mechanisms in case something goes wrong and a bridge fails or something like that, right? But assuming that everything is working fine, the bridges are up and running, this port is going to remain disabled, and so it's as if that particular connection is not there. Okay, this particular switch is going to be deaf to what it receives here, and it is not going to forward any frames over here. Okay, so it's as if we have broken the loop by removing this particular connection over here. Okay. So we end up with a tree. In this case it's very simple. But even in a very complicated graph, this is going to ensure that you have a connected graph. I mean, even after removing the disabled ports, everything is going to be connected. All the LANs are going to be able to send frames to all other LANs over this spanning tree that we have created. Okay, so let's fill in the gaps. Let's talk about electing the root bridge and so on. So how do we elect a root? So first of all, each bridge has a bridge ID. And the lowest one, the particular bridge with the lowest bridge ID is elected as the root. So what does the bridge ID look like? So first of all, there is a configurable part. And this is 2 bytes long. And then you have 6 bytes, which corresponds to a MAC address. Okay, so this could be, for example, the smallest of the MAC addresses of all your ports. Okay, I couldn't find the exact rule for how this particular MAC address is chosen, but essentially each particular bridge has to have a unique MAC address which is puts in here, and intuitively it makes sense to choose one of the hardware MAC addresses of one of your cards. Okay, that's going to ensure that everybody has. So this is, let's say if we use this particular method to choose this MAC address, the smallest MAC address of all the ports on that particular switch. This is determined for all particular bridges. But somebody may, let's say the network administrator may want to force a particular bridge to become the root for some reason or the other. You know, maybe that particular bridge is more well connected to the rest of the network, and it makes sense to have that particular bridge as the root. So this is configurable, and the default value is 32768. But you can choose any number between 0 and 61440, and you're allowed to use multiples of 4096. Okay, so that is what the rule says, and there's probably a historical reason for why they have chosen this. Okay, so fine. So we can choose this configurable part, and of course this MAC part comes from the hardware of the device. Okay, and by default all of them have the same configurable part. Okay. So if you want a particular bridge to have a higher priority of becoming the root, then you will put a smaller value. Okay, so everybody has a bridge ID, all the bridges have a bridge ID, but how do they elect somebody as the root? Well, obviously what they're going to do is they're going to tell what their bridge ID is. So when we have the election protocol running, each of them is going to broadcast messages in the following format. So each bridge tells its neighbors, it sends out messages of this format. YDX And what this means is that I think that y is the bridge, who I am hearing. Let's say the smallest ID I have heard. And this is my ID, and this is my distance to the root. Let's say distance to y. Okay, so what do all of these do? So let's assume that switch 1, let's say it has, just to simplify it, let's say that it has ID 1. Okay. So switch 1 is going to tell everybody that I am 1 and my distance to 1 is 1. This is the smallest ID that I have heard. And similarly, all tell their neighbors that I am the root. So initially they start out saying that I am the root and my distance to myself is 0, of course. Now let's see what happens. So bridge 2 and bridge 3, they are going to hear this message from 1 and they realize that there is somebody now who has an ID which is smaller than themselves. So they say that this is the new smallest ID that I've heard. 1 is the smallest ID that I've heard. Okay, and my distance is 1 to them. So then switch 2 says that I have heard 1, who is the smallest ID that I've heard till now. Okay, and my distance is 1 and I am of course 2. And what has happened over here, let's think about switch number 4. Okay, so we are still in the step 1, so this is not disabled. So switch 4 hears initially from switch 3 and switch 2. It hears these messages where they are saying that they themselves are the root. Right? They are saying that my own ID is the smallest ID that I've heard till now. So it sees that this is the smallest ID, so it's going to tell its neighbors that I have heard, the smallest ID that I've heard is 2 and my distance is 1. Okay, so exactly what happens, of course, depends on the exact time at which they receive messages. Okay, but let's say that switch 4 has not heard this till now. So it has only heard these messages. Let's just write it down that way. So after hearing from switch 2 and switch 3, it thinks that 2 is the smallest ID and it has distance 1 and it announces itself as 4. Right? So eventually this is going to converge So switch 1 is going to say 1, 0, 1. Switch 2 will say that 1 is the root. I am distance 1. Switch 3 says that 1 is the root, I am distance 1 and I am 3. And switch 4 is going to say that 1 is the root, I am distance 2 and of course I am 4. Okay, so this is how it proceeds. Okay. And to summarize the election procedure, so let's say that there's a particular node, let's say X, and let's say that there is another neighbor Z, so this is another switch, they are neighbors of each other. And X is aware of some other node Y, which it considers to be the root at the current stage, right? So X is sending message of the form Y dx, and d is the current shortest distance that it is aware from itself to Y. Okay? And let's say currently Z has some node which it thinks, let's say that we call YZ the current root, that Y thinks that, I beg your pardon, Z thinks that YZ is the current root, and it has a distance here, this much to YZ, and of course this is what it advertises. Now if YZ is less than Z, if Y is less than YZ, then what does it do? Then it has to set YZ equal to Y and DZ equal to this distance plus the distance between X and Z. Okay, and instead of, if suppose this is not true, but if Y is equal to YZ, so it's the same root, but the distance is actually smaller, so but let's say that D plus distance from X to Z, and this distance is less than dz, the current dz, then we update dz to be equal to this. Okay, so this is how we proceed until we converge to a root. So everybody should have the same root. Okay, so this is about the root, and what about the other part? So how do we decide about the root port? So suppose there is a particular switch, and let's say it has 3 different ports, and the distance to the root is, let's say we call this D1, D0 and D3, sorry, D2. If one of them is uniquely smaller than the others, there is only a single one of these which is the smallest value, then you choose that as the root port. Okay, so that's the obvious case, but what if more of them are equal to each other? What if D0 is equal to D1? Then which of these do we choose? Okay, so then there is a tie-breaking rule to choose. So what you would do it based on ID. So you would say who is this neighbor, and you would choose that one who has the smallest ID. Okay, so if more than let's say one port has the same smallest distance to root, then you tie break, you break the tie, based on ID of neighbors on the ports. Okay, so what we are going to do is we are going to choose the smallest ID. Okay, so D0 is the same as D1, and let's say that this has ID X0 and this has ID X1. And suppose X0 is less than X1, then this would become the root port. D0 is equal to D1, and these are less than, let's say, D2, and X0 is less than X1. Right, so that helps us decide the root port. And what about the designated port? So suppose there is a LAN and there are several switches connected to it. So one of them is the closest to the root compared to all of the others. Then that particular port connected to this LAN is the designated port. Okay, so suppose the distance to the root was, let's say that this is D1 and this is D2 and this was D3. Okay, this is all the distance to the root from these different switches. If one of them is the smallest one, uniquely the smallest, then that, let's say D1 is less than D2 and D1 is less than D3, then this becomes the designated port. But if two of them are equal, then we have to tie break, and again we'll do it based on the IDs. Let's say if D1 is equal to D2, which is less, and they are less than D3. Then tie break. Based on ID. Let's first call this switch 1 and switch 2. Okay, then we tie break based on the IDs of switches 1 and 2. Okay, so that's roughly the protocol that we follow in order to determine which are the designated ports and which are the root ports. And any port not a designated port or a root port is disabled. So there's one more thing I wanted to mention, and that is that in practice we can actually configure the weights which represent the distance between various switches. Okay, so the distance between two neighbors. So suppose you have two neighbors. Okay, and if the link between them, if this is, let's say this has a particular speed, you can give more or less weight depending on the speed. So normally this is what you do. So if the speed is 10 Gbps, so it's a really fast LAN, then the cost is 2, and if it is 1 Gbps, we give a cost of 4. Okay, and 100 Mbps and 10 Mbps get higher weights, 19 and 100. Okay, so distance is not just the distance in terms of number of hops like I've shown in the example above, but the distance would be given based on the link speeds. So essentially the idea is that you want to give more priority to higher speed links than lower speed links. You would like your data to travel over higher speed links compared to lower speed ones. Okay, so the algorithm would work exactly like we showed above, but the distances are not 1, 2, 3 based on the number of hops, but essentially we use the cost over here. Okay, so somebody really tells you the shortest path, and the shortest path weight or the distance on that shortest path is just the sum of the costs of the links all the way up to the root. Okay, so this is how switching works in Ethernet LANs.